Okay, thanks. So it's my great pleasure to have the opportunity to be both a speaker and an organizer for this nice event. I think it has been very successful so far, and I hope that I won't ruin this event in my last talk. So I'll be talking about a result relating to what Professor Chaoyang Lu was talking on boson sampling. It's about approximating permanent of random matrices with some conditions where the mean is vanishing. And it's a joint work with Zhihan Jin, who is now at ETH, and Pinyan Lu from SUFE, Shanghai University of Finance and Economics. If you are interested in details, you can check out the archive number here. But I would only have time to give you some of the overall ideas in our result. So permanent is a very basic function, and for a matrix A of size n, and it's just defined as a exponential sum over all permutations and product. From each row of the matrix, you choose one entry and then take the product, and so it's a summation of exponentially many terms in terms of the size n. And there's a even more well-known quantity called determinant, and we all know that determinant is easy to compute and permanent is hard. And that's a beautiful theory initiated by Professor Leslie Valent in the 70s, counting complexity. So we now know that computing permanent is sharply hard, while determinant can be computed in B. So there's a very dramatic difference between the complexity of these two problems, and it's I think it's the motivation for many areas in complexity theory, including counting complexity. So Sharpie will be an important class, and roughly speaking, it's counting the number of solutions of a problem. Formally, you would have a function is in this class Sharpie if there is a Turing machine M, which takes two inputs. X is the instance, like you can encode a problem in a string, and then that's X. And Y is supposed to be a solution of this problem, and M is checking whether Y is a solution. And it's yes, output 1, then Y is a solution, and we count the number of solutions to this problem. And if f of x is exactly equal to a number of solutions, the function f would be in the class Sharpie. So that's a computer science perspective, and in physics, interesting connection is that determinant and permanent are connected to non-interacting fermions and bosons. When you write out the wave function of the systems, and these quantities appear naturally, and I think it's a very famous joke that Avi Viktorson once made about this fact that bosons get the harder job. Because computing permanent, that if you want to understand the properties of bosons, you need to compute permanent, and it's computationally hard. So the reason that we're talking about permanent, it looks like a very mathematical problem in a quantum computing conference is obvious, because you have already heard about what Professor Chaoyang Lu's team is doing, and the rigorous connection is was proposed by Professor Scott Aronson and his student Alex Arkhipov back in 2011. The published version is 2013, but the initial version appeared in 2011. So it's 10 years, a decade ago. In that paper, that's one sentence from the paper, that they say that their main technical contribution in that paper is to build a connection between the ability to between the ability of classical computers to solve Boson sampling problem and the ability to approximate the permanent. So basically, there's a connection there, and that's how it's all connected. And as Torian has mentioned, this is a very a well-respected achievement, and Scott Aronson got his ACM prize partly because of his work on boson sampling, the proposal that initiated this line of research. So a bit more background: what is boson sampling? It's a sampling problem from a net, like given a non-interacting boson network. You send in some photons, and you need to simulate what you would see at the other end. It's very rough theoretician's imagination of what happened here. But the motivation of study such a very special problem is to challenge extended Turing thesis on a near-term device. We know that the first example that as a candidate to challenge extended Turing thesis is Shor's algorithm, because Shor gives an algorithm to factor big numbers on a quantum computer efficiently, and we believe that this cannot be done on a classical computer, and that's a candidate that we can show that it's not the case that the classical Turing machines can efficiently simulate all physical computing devices. And but there are two limitations from Shor's candidate. One is that we don't have a good theory for the hardness. It's just a belief that people have tried many years. Sorry, the light. A problem controlling the light, it goes out after a while. So Shor's limitation candidate has a limitation because we don't have a very solid grounding of the complexity of factoring problem. So not as solid as the one that we will have for boson sampling, at least. And also it requires a large-scale error-corrected quantum computer, which may be decades away. Boson sampling is in one of the few so-called quantum supremacy proposals. We want to do something that in the near term that on a quantum computer, the classical computer cannot simulate. And there are other examples, IQP sampling and random circuit sampling that Google team choose to use on their superconducting platform. They all share a very similar structure. You prepare some initial state, you apply some circuit, and then you measure all the quantum bits or particles in your system, and you get a distribution. And you want to sample from that distribution, and that's the sampling problem. So a bit more mathematically, you would consider a matrix A of size m rows and n columns. So this is a matrix of column orthonormal. So each column is a unit vector, and each column is orthogonal to each other. You would consider an asset which is a partition of n into m numbers. So this m is in physics term modes, number of modes. SIs are integers larger than or equal to 0. They sum to n, and we define a submatrix or sort of submatrix AS from A by taking SI copies of the ith row from the matrix A to make an n by n matrix. For example, here we take this 5 rows to make a 5 by 5 matrix. And then we can define a probability distribution in this way. So it's the permanent of the AS squared divided by this normalization factors. It's maybe hard to see why this is even a distribution in the first place, but yeah, so that's how it's defined, that we want to sample from this distribution, and the fact that this is actually a distribution follows from the property of matrix A, that we have orthonormal columns in that matrix. So mathematically, it's a very simple problem. You have a matrix. You can take some sort of a submatrix, but you can repeat the number of rows. If for example, if SI equals to 2, then this row would appear twice in A, and that's the way we form this matrix A. and then we assign probability to this partition, which is given in this quantity. So that's Boson sampling problem. The reason that the connection that Aronson and Arkhipov made is that assuming two conjectures about this matrix permanent problem, then a very interesting claim follows, which says that if you can have a classical algorithm that takes this matrix A and parameter epsilon as input and samples from another distribution, which is very close to the Boson sampling distribution that we want to simulate, in polynomial time in the size of matrix and 1 over epsilon, then the polynomial hierarchy collapses. So maybe I've seen this figure about complexity classes in Professor Zhang's talk earlier in the afternoon. So polynomial hierarchy is union of a bunch of classes like from NP and NP with an NP oracle and so on. And so that's the polynomial hierarchy. And above that, you have P to the sharp P, which is basically characterizing the power of sharp P counting problems. So it's in complexity theory, it's a very well-known result, total theorem, that counting is very powerful. P to the sharp P contains polynomial hierarchy. But on the other hand, complexity theorists believe that, like as in our belief that P is not equal to NP, we also believe that this power in the hierarchy, in polynomial hierarchy PH, does not collapse, meaning that there's no finite level of this powering, making oracle calls, so that it saturates the power of a polynomial hierarchy. You can think of this as a belief that in computer science, theorists believe that it won't happen. So then what this says is that there should be no classical algorithm to sample even approximately close with equivalent distance to the output distribution of the Boson sampling problem. But the catch is here, like you need to assume two conjectures, and that's actually what we need to get into, talk about more about that. So there are two conjectures, and we are focusing on one of them. That's the base, the permanent of Gaussian conjecture called PGC. So you have a matrix X, and it's n by n, and the entry is complex numbers, but it's a Gaussian random number. You have mean value 0 and variance 1. That's input, and your problem is to output a number to approximate permanent of X to within multiple error epsilon. So you can output a number which is within this plus minus epsilon permanent X error with high probability, with probability 1 minus delta, and efficiently. So that's the problem of so-called Gaussian permanent estimation. The time scale is like multiplicative approximation. So a conjecture that called PGC is that this is a hard problem. So you cannot do that. Given the matrix X, there shouldn't be efficient way to do that. And actually, it's sharply hard. And we want to show that if you can do that, then you can do all the sharpie problems. Okay. There's another conjecture called anti-concentration conjecture, and I won't be getting into details because it's not relevant to this talk. It's also, I guess, less interesting because it's relating the multiplicative approximation to the additive approximation. So what really is important to the Boson sampling conjecture is the permanent of Gaussian conjecture. So it has been proposed 10 years ago, and still we don't know whether it's true or not. And we'd like to have some understanding of that problem. One thing that I should emphasize that the problem has a property or a feature called like it's a particular problem called average case approximation problem. So it's average case because we have a distribution and we only want the algorithm to be successful with high probability, 1 minus delta. We are not required to work for all the input instances x. Like in an alternative case, you would have worst case problems where you would require that the algorithm is correct for all inputs. But here we have a distribution and we only want the algorithm to be correct with some noticeable probability. So the other part of the problem is it's an approximation problem. You can tolerate some error. You are not required to return the number permanent of x exactly. You're just allowed to have some error, and error is multiplicative up to epsilon. And so actually, I should mention that this is a common theme of assumptions used in different quantum supremacy proposals, IQP and random circuit sampling. They all share kind of a conjecture where it's in this flavor. You have average case and approximation problems. And it's important because from like if the problem is not the you have two average case and approximation. If you consider, for example, average case exact computation, then there are a lot of methods to show Sharpe hardness, and it's a very interesting technique that you can do some interpretation. So if you are interested in permanent of M, you can take a random matrix K and consider the permanent of M plus XK, and you would try to argue that there are values you can evaluate the polynomial of permanent of this matrix in terms of x is a polynomial in x, and its degree is the most n, which is not too big, hopefully, and then you would evaluate this polynomial on more than n points, and you would determine the polynomial, and then you take evaluate the polynomial at value x equals to 0, you get the permanent value. So there's a standard approach to do this reductions from Sharpe hardness to average case exact computation, and this is also in the beginning it's for finite fields, but the similar ideas can be generalized to Gaussian entry, like with complex numbers in Scott Aaronson's and Archipov's paper. So the difficulty for generalizing such a technique in this approximate and average case scenario is interpretation of polynomials is very sensitive to noise. If you're not returned exact data point, then the interpreted polynomial would be dramatically different from the one that you want, and that would be a big problem for following this approach in this average case approximate problem for permanent. But why do we believe that such a conjecture is true? There are many justifications, and you can check out Scott's paper if you are interested. But I guess like one of the main intuition, like we tend to believe this is true, is because cancellation in the definition of permanent. So this is way that you have written down the permanent, and because these entries they are complex number, even if they are real numbers, they can be plus and positive and negative, then there will be massive cancellations when you take the sum. Right? It's not you're adding up positive numbers, but you're doing addition and subtraction all the time. And actually, like as a comparison, if it is a case that the matrix A has all non-negative entries, then we can actually approximate the matrix permanent to within multiplicative error efficiently. And so that sort of justifies that it has to be considering a matrix with both positive and negative entries. And our belief that this is hard is because cancellation happens. And because cancellation is so important in quantum algorithm and speedups, For example, in quantum Fourier transform, there's a lot of cancellations happening. That's believed to be the reason that quantum algorithm has an advantage. So looks like we are grabbing the right point that making the quantum devices powerful. Cancellation in Boson sampling is also the case that we believe that's a reason for the hardness to classically simulate this or classically computing this permanent. But returning to the main topic, in 3 years ago in FOCS, Elder and Maharaban, they proposed a particular approach to this problem. They want to solve the PGC, but they cannot solve it directly, so they proposed a modification to the problem, where the modification is simply that instead of truly zero-mean Gaussian, they considered entries, random entries with a mean value mu. For example, mu is just some positive number, but it's vanishing, and I guess the cancellation still happens because even though you have larger probability to have a positive number, there is still a constant probability of having a negative number. So the entries can be negative and positive, and cancellations do happen. So you cannot explain that whether or guess whether you can actually efficiently approximate this new problem. And what surprisingly, they proved that if you take this mu to be 1 over polyloglog n, then they give an algorithm to refute PGC in that particular setting. And interestingly, they also show that if you can improve this mean value to 1 over poly n, then you can actually solve this PGC in the negative, and that will be a crisis for the community that we have to think about other candidates.
So a quick question: what is PGC?
The conjecture that I mentioned, the permanent of Gaussian conjecture. So okay. Given matrix X, where actually the mu, if mu is 0. And you want to approximate the permanent in this average case approximate sense. So that's PGC. So the only difference here is now you have a mean value that's positive. But like the mean value is when the system side, when the matrix is growing, the mean value goes to 0. But it's not fast enough. What we want in PGC, something equivalent to PGC is 1 over poly n. But what they can show in that FOCS paper is 1 over polylog n. So it's double exponentially gapped between what we need and what we proved. So so that brings me to our result. So we have exponential improvement on the mean. We can prove that for 1 over polylog. You can still have efficient algorithm to approximate that permanent. We also are a bit more general than the result. They proved this for Gaussians. We can handle a large class of distributions over complex numbers, and you will see the condition. It's a very general condition. And also we have a much simpler proof. In their case, they used the very popular Bavinoch's approach. You analyze the roots of certain distribution of roots of certain polynomials, but our proof technique is just truncate a series that's very brute force, but works even in a better give us a better result. But like the common ground that we share is a mathematical paper, Rampala and Wesolowski, where they studied the limiting behaviors of permanent random matrices. Okay, so the problem setup, we want to consider PGC where the matrix entries has a mean value mu and variance 1. So we can do a scaling. So divide by mu, then mean value is 1, and the variance is now mu square inverse. So because the mean value is always 1, we can write the matrix Y in this form, so J plus Zx, where J is all ones matrix. We take all the mean value 1 in matrix J, then this X part is a random matrix where the mean is 0, right? So we have a X random matrix where each entry is sampled from distribution D, where the distribution D has 0 mean, variance 1, and bounded third moments. So that's the condition that we need to make the proof work. You can see that it's a very general condition because Gaussians, Bernoullis, and most reasonable distribution will satisfy this condition. And because we are considering matrix Y, so J gives you mean 1 and the variance is Z squared. So that gives us, in the end, we will choose Z to be 1 over mu, and it will be polylog because we want mu to be 1 over polylog. So Z will be a polylog large number. So given such a setup, what we want to do is to have an algorithm that computes approximates Y's permanent with multiplicative error epsilon in most cases with high probability, because there's random procedure choosing the matrix. The algorithm should work for most Y's. Okay, so how do we prove that? First we use an expansion in this form. The permanent of J plus Dx, this is Y, this is the matrix that we care about. You can expand it. First of all, this is like a polynomial in Z, right? So you can write it as a polynomial AK ZK, summation over K from 0 to n. And this you can exactly compute the coefficient AK as a summation of smaller permanents. So permanents of matrices B, where the B is K by K submatrix of X. That's a very simple fact that you can verify up to some normalization. So that's how you define AK. If you are able to compute these small permanents, then you have the coefficients, and so that's how we define this expansion or series. And then the idea is then we truncate the series. So we would choose a T. So previously it's summation from 0 to n. Now it's 0 to T, where T is only log n over epsilon. And we want to use that number. So you compute this thing and use that to approximate this 1 over n factorial permanent of this matrix. So if you study the running time of this algorithm, you would from 0 to T, this is T here, and we will choose AK is defined by the permanent of some matrices. So you choose n choose K, so from rows, and n choose K for the columns, and that gives you the matrix B. And then in T factorial time, you'll be able to compute the permanent of the small matrix. So basically, that's the complexity. And if you do some algebra, you know that it's n to the 2t. And so it's a quasi-polynomial time algorithm. It's not polynomial, but it's not n to the some constant, but it's n to the log n. But like for this claim to work, we need to two things. One is that the tail is small, right? The t plus 1 to n is at most this quantity, and this first two t terms, t plus 1 terms is big. That's two part, and actually this easy part is a small tail. Proof by definition of this AKs, you can easily compute the so-called covariance between AK and AL. The expectation of AK and AL bar. This is a complex conjugate, and that's exactly 1 over K factorial delta KL, where it's a Kroneck notation. So if K is equals to L, it's 1 over K factorial, otherwise it's 0. And the reason that, for example, if K is not equals to L, It's zero is very simple because so A is like a summation of permanents, and permanent a summation of degree k monomials, right? If it's a degree k monomial and AL is degree L monomial, and when you take the product, because k and L are of different lengths, there will be at least one variable that is not square, right? So then the expectation of that variable would give you 0 because the x has 0 in. Using that, we can easily compute the variance of the tail, and that's small. So that's gives us, using Chebyshev inequality, you would know that with high probability, this tail is small. For the other part that we want to argue that the leading terms are actually big, that's a much harder problem. What we do is, first we will use a so-called column sum approximation. It's a very simple algorithm. You compute, you have the matrix here, X, which is as mean 0 matrix. We have taken the mean 1 to the J matrix. So for this X matrix, you take the column sum. So for the J's column, x1j to xnj, you take the sum, and you normalize by square root n. So for example, if these are Gaussian independent Gaussian numbers, then normalizing it with square root n is still a Gaussian of the same variance. So you can think of Cj as a new random variable. It's depending on the column sum. And we'll introduce a quantity called Vk to approximate Ak. And Vk is just you take k different columns and multiply the column sum together and do some normalization. And we claim that Vk is approximation of Ak. So why is that? But because Ak is a summation of permanents, and the feature of a permanent is all these terms are they are monomial. They are terms from different columns and rows, right? And if it's Ak, it's k by k. So it's and it's k by k, and it's from different rows and columns. But Vk is a slightly different thing, because, for example, if k equals 2, as in this picture shows, Vk is then the column sum. You take two columns, take the sum, and multiply them together. You would have, for example, when you expand this thing, you would have terms like this, like these two green entries multiplied together. And that's good, because that term should also appear in Ak, so that's a good term. But in the bad case, you would see two entries appearing in the same row, and that never appears in Ak, so that's an error. But the intuition is this thing won't happen very often, because you can think of this as a random procedure. You can have n terms. You choose two randomly. You don't expect to see two terms that have the same row index. So in that sense, Vk is a good approximation of Vk, at least for small k. So that's for the first approximation step. So Vk, as its definition, it's a summation of different columns. And if you think of Cj's as variables, it's so-called elementary symmetric polynomial of the column sums. And it's I guess it's a well-known fact that you can expand this elementary symmetric polynomials in this form. It's called Newton's identity. You can have a recurrence relation that computes Vk in terms of the previous terms and dk, where dk is a summation over Cj to the kth power. Okay, like the most simplest example is xy equals x plus y times x plus y minus x squared minus y squared divided by 2, right? That's k equals 2k. So you can generalize to all k, and that's called Newton's identity. So our next step, we have another approximation. we observe that vk is defined in this way, but like this d2 and dk has very nice concentration properties. So d2 is concentrated around its expectation value we call psi. If you do a calculation, you would know that expectation of d2 is exactly expectation of x squared, where x is from the entry distribution. So note that x can be a complex number, so it's not the variance. It's just some second. It can be a complex number, but it's concentrated around that because the normalization here is n. It's not square root n. So that's why if you compute the variance, it's very narrowly concentrated around this number psi. And for higher order terms, for k larger than 3, we can prove that dk is concentrated around 0, because now this term, because in the definition of dk they have you have n to the k over 2 here, so it goes, this term would dominate, and you would have a very a good bound on the absolute value of dk. So you can think of this as 0, and this is psi, a fixed number. And so we use that to further simplify the recurrence relation. We define a sequence called vk prime, where we just replace d2 with psi and replace di plus 1 with 0, and that's a new recurrence relation. So essentially this sequence only depends on the value of v1. So you start with 1 v1, and then you can compute all the future terms. So to review what we have been doing, we want to give a lower bound. So the leading terms are big, but we have choose to approximate ak by vk, and then approximate vk by vk prime. So we show that with high probability that these two approximation hold. AK and VK, if we switch from AK to VK, the error is small in terms, like thinking about the leading term summation, and similarly VK and VK prime have small difference. So in that sense, we have reduced the problem of bounding this term to bound the absolute value of this term. And again, by a tail bound, it suffices to bound this infinite sequence from k to k from 0 to infinity, and vk prime zk. So that's what we want to bound. We want to make sure that this thing has a not too small absolute value. Okay, so how do we do that? We need to use a tool called Hermite polynomials. There are two versions. One is called probabilistic Hermite polynomials. The other called physicist polynomials, Hermite polynomials. And so the definition of this polynomial is in this way. So it's funny looking that you have exponentials and looks like some Gaussian, but you take the derivative. What's interesting that these are actually polynomials. I mean, when you plug in k equals 0, 1, and you can compute that these are very simple polynomials. And the interesting thing about this polynomials, there are many interesting properties that you can check out on Wikipedia. But the two properties that we use are, one is about the recurrence relation. So you can alternatively define this Hermite polynomials in this way. So the k plus 1's term equals x times the previous term minus the previous term's derivative. And also the sequence has an interesting generating function. So if you consider ek x as the coefficient, and take tk over k factorial and take the sum, it's equal to the exponential of xt minus t squared over 2. So that's an interesting fact to know. And using these two conditions, we actually see that the vk prime sequence that we define is nothing but the polynomial evaluated on this v1 over square root of xi. It's not hard to see because this recurrence relation is very much similar to the recurrence relation of vk prime. And then using this generating function property, so this is a very good convergent approximation of a way of computing this infinite sum. So we would be able to write explicitly the sum vk prime zk as exponential to the v1 z minus xi z squared over 2. So it's explicit, it's some sort of exponential. And then we can show that this thing is large by arguing that v1 is small, right? The thing that this thing can be small is it is exponential to some very negative large number, and we argue that that number won't be too large; it will be some small number, and that's how we bound this term here. So that completes the proof of the leading terms have high value, and that completes the proof. So to summarize, I've told you that there is a quasi-polynomial time average case approximation algorithm for the random permanent problem, and it's for a very large family of random matrices with mean. You didn't see this, but like when we choose this parameter z, or in all our approximations, it's polylog n, so mu would be 1 over polylog n. It is an exponential improvement over previous result where it's 1 over polyloglog n, but it's still exponentially far away from disproving the conjecture PDC. And personally, I feel that this is a very interesting problem because it's elegant and you just have a permanent, and but looks like you need some new ideas to prove that. And I think from this perspective, like you can think of this as a transition of hardness depending on the mean value from the mean value of 1 minus 1 over polylog n that we have been able to prove that this problem is easy. And if PGC is correct, then when this sin is 1 over poly, it's sharply hard. Then there has to be a point where you transition, you have a transition from easy cases to the hard cases, and it's interesting to find out whether you have a transition or actually the PGC is not correct. So thank you for your attention. I'm happy to take